And we're back. Welcome back and happy Thursday. Today we will focus on the implementation of regression in Matlab. But before we begin, some administrative bits, the reading, video, as well as a PDF on least squares regression, which is on the Blackboard. When we last left off, we talked about the credit score problem. And in this, we input our vector-valued features for our in-sample data, our historical customer records. And with our linear function, our hypothesis, our weight vector, we compute the weighted sum, which results in a real value that we call our score. Now, this real value pertains to the credit line amount for which that customer, defined by their input vector, is described. And so we talked about an example in feature space, and here the horizontal axis was the amount student loan, and the vertical axis was the output of the ground truth target function, that label, that real valued label. And that real valued label is the credit amount associated with each one of the customers from historical data. And in this case, the customers are defined by a single attribute, namely the amount of student loan debt. And so then we said we want a linear hypothesis, and a linear hypothesis, line on the plane in this particular example, we want one that best describes or mimics the labeling of our target function. And so we measured the difference or residual between the predicted real value for each input, or each customer, and the ground truth label assigned by this unknown target function. And so this residual could be negative or positive, and we care about the magnitude and not the direction when we're trying to fit the best linear hypothesis to the data, i.e. to mimic the labeling of the unknown target function. And so we computed the average set of residuals using what we call the squared error loss function, because we don't care about the direction, whether that loss is positive or negative. We care about its magnitude, so we square it. And so we take the average squared error loss, that difference between the output of our working hypothesis on each one of our historical data points, records, and the ground truth target function's label. And so we coined the term in-sample error, or EN, as this average squared error loss. And we gave an example of a one-dimensional feature where a customer record is defined by a single attribute. And we also talked about a two-dimensional feature. For two-dimensional feature, our linear model is a plane in more than two-dimensional feature space, or for two-dimensional features or descriptors for customer records, we call it a hyperplane. And so here we looked at how you would depict and measure residuals for both the one-dimensional feature example as well as the two-dimensional feature example. Okay, and so we ended up with our linear regression solution, and we outlined the algorithm for how this linear regression algorithm plays out. So you take your data and construct design matrix X, and this X is a row matrix where each row consists of the transpose of each one of our input records in D dimensions, and these vectors you can assume are column vectors. Hence, we have the transpose as each one of the rows for our design matrix. And then we also have the target vector consisting of all of the ground truth labels from each of these big N many customer records. And so from this, we took our expression for in-sample error in matrix vector format and computed the pseudo-inverse, which solves for the W where this squared error loss is minimized. And we got that by setting the gradient of in-sample error in vector matrix form to 0 and then solving for W. And so with this, let's go to Matlab and take a look at an example of doing this on a data set. And so the data set we're going to use is from a public source, and it has real estate information for King County, Washington. There's King County, Washington. And so it consists of a set of features or attributes. Now, these attributes, the most important one to pay attention to is the price. That is going to be the target, that ground truth class label, or that label associated with each input by the unknown target function. And that's what we're trying to find, a working hypothesis that mimics each one of these real valued labels. And so we have all of these attributes that define a house. The ID, of course, we're not going to use. The date of sale, we're not going to use. But all the others we will. The price, that's going to be our target value. And then the remaining attributes or features, from the number of bedrooms on through square footage of the land lots for the nearest 15 neighbors, those are going to be our attributes that collectively comprise the description of a home. And so each one of these vectors has these descriptors for a different house. And now what we set out to do is find, through regression, that best hypothesis that solves for the W that matches as closely as possible this price. And so that's what we're going to build. All right, so let's look at Matlab. I will meet you in Matlab. So we're here in Matlab, and we start out with our KC house data.csv. We read in the CSV file, and then we set the random number generator with a seed 0 using the Mersenne twister. Now, we set a seed of 0 because we're going to change a few things for the experiment, which particular features we use to describe our house data, customer records, our historical records, and we're going to rerun it, but we want to make sure we get the same random number sequence. And so we have this variable that created, show correlation. I'm going to set that to true because I want to show you the correlation, linear dependence pairwise between variables, and we're going to use that as the basis for selecting the set of variables that we use to describe each one of our historical data records. So you don't have to use all of the features. We're reducing it using a kind of rule of thumb based on correlation between each of the features and that price, that ground truth label. So we start out and we read the CSV file into memory as a table in MATLAB. And tables are a data structure that has the names of the field types. It makes it a lot easier to deal with. And so the first thing we do, we read it in. This is called XRaw. And then there are some records or some vectors or houses described by a vector where one of the fields is not a number, meaning undefined. And so we decided to take the data set and augment it, to clean it up by removing those vectors, those descriptors of houses where one of the features is unknown, not a number value. And so we call this remove missing, which cleans up our data set, removes those records that have missing values. And so now we make some measurements, and then we take out the real estate ID and the date. We don't need those to predict the price of the house, so they're not necessary. And then if you go into the table, some of the column names, the feature names, have an underscore character in them, and that kind of throws a wrench of sorts into the descriptor for the labels when you compute pairwise the correlation or the correlation matrix between these features. And so I set some new names, equivalent new names, removing those underscore characters, and then I rename the column names in the table using rename variables. So here I rename variables on line 46. You give it the data, cleaned up data, that has had those date and the real estate ID columns removed, those features. And then we have the current names and their replacement for the new names. And that's going to be my cleaned up version of the data. So now with show correlation, we come down here, show correlation is true, and we're going to call correlation plot, and that's going to bring up beautiful pop-up. And on the diagonals of this matrix, correlation matrix, we have a histogram visualizing the distribution of each of the variables. And then off diagonal, they're going to be the correlation values as well as the correlation plot, both a scatter plot with the best line fit to show the correlation. And so we show that graph, and it's going to take a little bit of time because of the amount of data that we have. compute correlation, you need on order of n squared correlation computations, where n is the number of features. And so then after that, I went through ahead of time and looked at highly correlated features, features that correlate well with the price target, that label assigned by the unknown target function. And so I removed them, and this is the beauty of using tables in Matlab. You give the name of the table, dot, and then the name of the column name, which is a feature. And it makes it much, much easier to manage extracting individual columns out of your data. So I pull out a few of them, and then I create a new version of the data table using various combinations, some smaller, some larger, of these individual columns that correlate highly. So then after that, I take a new measurement of the resulting data set. I call it the data. And then I select some number of them, in this case 5, and I pull them out of the table. I set them aside, and that's what I'm going to use to test out my regression. Once I get my final best hypothesis, my weight vector, I then use that on the new or the set-aside instances, my test data, and then compare the prediction of that final best hypothesis on that test data with the ground truth label. See how far off it is. So I do that, I make a selection, and I remove them from my data table that's been cleaned up and had first 2 columns removed, and then I call that test data, set it aside. And so now I isolate the vectors from the test data. Those are my test vectors, and I isolate the ground truth labels associated with that test data, because I need those labels in order to make the comparison of the ground truth, which is y_test, with the prediction, which is the final best hypothesis, G, evaluated on these test vectors. And so then I take my original data and I delete those rows, those entries that correspond to the set-aside data using those indices that I randomly selected. So now I construct my design matrix, that same X matrix that we talked about in the algorithm for regression, and then I also set my target vector, y_vec, and that's going to be the set of labels. And so I compute the pseudo-inverse, which is just X transpose X times X transpose times Y, our target vector. It's exactly like we talked about in our expression of the algorithm for linear regression. So now, taking my W value, that's my final best hypothesis, I then loop through my test set. I extract a new vector. Now, this new vector is not in the data set that I use to compute the pseudo-inverse, so it's, for all intents and purposes, is acting like a brand new house that comes on the market. You describe it in terms of all of those attributes, and then you run your best hypothesis, and it outputs some h of x, which you accept as your predicted price for this particular home, described by its vector value. And so once we make this prediction, h of x, w transpose x, that new vector, we compute the error, and this error is the difference between the hypothesis evaluation on that new value, h of x, and this target vector, this target value, which we got from the target function, that label, ground truth label. And then we print out a message, and we do that over all of those set-aside test data. Okay, so let's go ahead and let's set a breakpoint. Why don't we just run this through? We will first look at, let's set a breakpoint right where the correlation is done, and we'll do that by setting a breakpoint here on our expression for the pseudo-inverse. So let's set the path, make sure that we have that path. Okay, so let's set a breakpoint on pseudo-inverse. Let me run this. So now it's going to take a little bit because computing that correlation matrix is a fairly heavy-duty computation, but it's not so bad, and it should pop up in the next maybe 10 or 20 seconds. And so here, this correlation matrix, it's a very well done visualization, and it's done as one of the Matlab APIs, and it computes the correlation pairwise between all the features. And again, stress that it takes a long time to run on order n squared, where n is the number of features. So let's go ahead and let's take a look at our correlation matrix. It takes a little while to pop up. Here it is, figure 1. And so let me blow this up so it's a little bit more visible. The redraw can be slow sometimes. So let me blow that up. And we'll just let the graphics system catch up a little bit, and it will make this plot a lot bigger. And so here we have our correlation matrix. Along the diagonal, as I said before, you see the histograms visualizing the distributions of each one of these variables. So we have price, we have number of bedrooms, we have number of bathrooms, we have square foot, we have whether it's a water view, the number of floors, the grade. It's a score assigned by the local community about the quality of the housing, the latitude, longitude, the square footage of the surrounding 15 properties. And so if we cast our attention here to this first column, right, that's price versus all the others. And so here we see that the number of bedrooms, number of bathrooms, and the square footage, they correlate pretty highly with price. 0.31, 0.53, 0.71. Here we have 0.40, that's water view, whether it's a view, it has a good view, and water, if it's in front of water, because properties in front of water are generally more expensive. Square footage, we also have here, if we look at latitude, correlates positively 0.31. Well, that has to do with the location. If it's in a desirable community, the latitude tends to be something that coincides well with the price, good predictor of the price. And so use this correlation matrix to pick the top few of the features that have a very strong or stronger linkage with the price. And so those are going to be, as we are going to deem, indicative of the price, or they are predictive of the price. And so let's go back to the MATLAB, and now we're going to compute the pseudo inverse to get our W vector. And so let's step here. We compute our pseudo inverse, so this is our W vector, and you notice it's a column vector. And now we go through and we take our test set, and we'll continue through, and we plot both h of x, y of x, and then the error. And so one of the things you'll notice, if we change the number of descriptors that make it into the description of our data, the dimensionality of our vector value quantities, you'll see that the error changes dramatically. Now, of course, we're only using a small number of them, and if we use the entire data set, we would see that our error decreases. And again, it's not perfect. We'd need a lot more data than the size of the data set we have. But this is an example of how you would implement the same regression algorithm that we talked about in our module on regression. So with that, let's pivot back. So we're back in PowerPoint, and we have here a picture of the attributes, and we just went over our implementation in MATLAB of this regression algorithm. We used the King County real estate data, and we then took our attributes and we selected some subset of the attributes to describe in a smaller dimensionality each one of our houses, just as vector value records from historical data, but we use the correlation matrix to inform us on which particular vectors are more predictive or tightly coupled with the ground truth label, i.e. the price. All right, so with that, that's all I had for today. Hopefully this was informative. And as usual, please stay healthy, stay safe, and I'll see you all on Tuesday.